Okay, our lecturer today is an eminent scientist, Bonnie Shoemaker from JPL, who has had several other careers in her life. She has been a concert pianist with the Walking Philharmonic Orchestra. She has been a professional model. She has been a captain flying 737s for Continental Airlines. And she is currently, and she got her PhD here at Caltech under Carlton Caves with me kibitzing on the side. She laid the foundations, mathematical foundations, for much of the work that's being done currently on QND designs for advanced flight interferometers. She's going to tell us today about her current work, which is on the disturbance reduction system for LISA. She's the person in the United States who is basically in charge of the design work and the noise studies for this disturbance reduction system.
None of that was true. Oh, I guess we don't have a chair. Okay. I want to talk about the LISA disturbance reduction system, which every girl cares about, how to reduce all the disturbances to her. This is a rough outline, but it will help you if you go back and if Kip gives you really nasty homework problems, you can... Oh, you'll find them. There are dozens. They're all over. But you'll be able to look at least for some references here. And there is a document, too, that I'll give the guys to put on the web if it helps you. Because not only there's a selfish interest here, not just that he's going to give you homework problems to make trouble for you, but there are some real problems that still need to be examined more carefully, and that we would really appreciate a double check on. And it's physics. It's really fun. When you go to looking at all the disturbance sources that could bother LISA, it really is physics 101, because every mechanical possible disturbance, every piece of electromagnetic physics, just about anything could bother her. Am I doing that flashing or? Good, thanks. So basically we'll go through a quick review of LISA. You've heard it twice now, but I'll review what it is and how it works. We'll go through the requirements on the disturbance reduction and the general approach. And then before I get into a lot of history...
Try going on to the...
computer too?
Click on this guy down there.
Oh, what was that? What was that guy?
Is it blinking on your screen?
No, it's not. The screen is constant.
You might need to set up the other projector.
Oh!
No, that kills it. Yeah, that switch shuts the whole system off.
Can we reboot?
That does a complete reboot.
No, it's smiling. I think it should work. It's without rebooting the computer.
10, 9, 8. And we should do this for landings. 3, 2, hit. Oh.
You know, it's supposed to.
That's good. Thank you. And then we're going to go into the control model and have some fun with some physics. I do this selfishly so that we get through the physics, even though it's harder equations, because that's what we'd love to have your help on, and it really is fun. And then down here, you'll have more pretty slides than history of heritage and ground demonstrations to date. And this is also some fun, not just the baseline design, but the options for different ways to do it. And this is where some real research opportunities come in. Okay. Oh, you know what? Now that it's different on my screen, I don't know how to go to the next one.
Just click the
Next.
No, just
Click the bottom one?
Yeah, just click your mouse button, left mouse button.
And the right one goes backwards?
Or this.
Oh, great. Great,
That's
thanks.
the simplest way.
Okay, just one more pretty picture to add to the 5 or 6 or 7 you've seen already, and a review. And I can see each of you have been here, so I'll go through really quickly. It's a constellation of 3 spacecraft, and each of the 3 spacecraft are in a 1-year solar orbit, 1% eccentricity, so it's just barely inclined to the ecliptic. And the whole triangle is tipped at about 60 degrees. Why do I care about that? That's because the normal of the solar panel to the sun is about 30 degrees to the sun around the entire orbit, which gives us a very stable solar illumination. And that's particularly important to the disturbance reduction, because that means the only noise we worry about is from variations in the spacecraft power and the solar flux. And the triangle center is about 20 degrees or 1/3 of an AU behind the Earth in Earth's orbit. That means about 50 million kilometers, and the arm lengths are about 1/10 of that, about 5 million kilometers. They don't remain constant relative to each other. It would be great if they would, but 20 degrees behind the Earth is not a Lagrange point. More like 60 degrees would be better. As a result, the arm lengths vary by about 1 or 2% over a year. And you've seen all this before. In fact, this is a prettier picture describing what the orbits do, as said on the previous one that Bill Fokker gave you. The measurement concept, you already know that as well. Each of the 3 spacecraft has 2 nearly free-falling proof masses. And they serve 2 purposes. Each proof mass, first of all, is a reference mirror to reflect the laser light from the other spacecraft. And secondly, it's a reference point, or one of 2 reference points that serve as a common reference point for drag-free control of the spacecraft. Of course, the spacecraft, first and foremost, is simply a shield around the proof mass to shield it from external forces. And we, as you'll see later why, we force it to follow the proof mass to about 300 picometers at nominal 1 millihertz. The position and the attitude of the proof mass with respect to its housing, which means respect to the spacecraft, because I'll assume that the housing is rigidly fixed to the spacecraft, they're monitored constantly. And the way the proof masses are kept centered in their little housing is twofold. One, you move the spacecraft along the measurement axes. We're just going to move the spacecraft and don't touch the proof mass. And along the other axes and out of the measurement plane, we actually do some limited actuation of the proof masses. All of this is fine, but at some point you also have to allow for a much more invasive actuation, suspension during launch for caging and then initializing on orbit. Once you get it there and you're ready to do science, you'd like all the active control that's invasive to move away. So there are several options for the sensing and the actuation. The first one, which is the baseline right now, is capacitive. It has a lot of heritage in accelerometers, but as I'll show you in a moment, LISA is not an accelerometer. And so some of the things that go into the capacitive accelerometers that have been built don't apply to LISA. But in that case, you have little tiny electrodes on the surface of the proof mass and on the surface of the housing, all around it, all 6 sides. And you apply voltage to the electrodes on the housing to change the gap. Other options are optical sensing. You can imagine a little diode laser here bouncing off the side of the proof mass and on here quad diodes and have those 3 or 4 sides or corners. Or gravitational sensing or actuation, which is a new idea that Tom Prince at JPL thought of and proposed last January, and we've just started to think about. That's something I'd like your help on later. It's a fun idea. Again, just a quick review, and also a way to tell you about some stages of thermal isolation. Here's one of the LISA spacecrafts with its thermal shield on the top, little end. So supposedly these are 30 centimeter antennas for telemetry, but they look pretty tiny here. So the first layer of passive thermal isolation, if you will, is the time constant of the spacecraft itself. Then there are these Y-shaped tubes, second stage of passive thermal isolation. And they enclose the optical assemblies you saw earlier. Everything is mounted from the thing it's mounted to with low conductivity thermal flexures, probably fiberglass, graphite epoxy. And then, as I said, since the arm lengths aren't constant, you'll have to change the angle between the roughly 60-degree angle by plus or minus 1 degree over about a year. So this is done with flexures at the base of the Y tube. And the lasers and the thermal radiation plate are mounted at the very bottom of the Y so that heat from the laser can go out the bottom of the spacecraft. Remember, every disturbance we can has to go away. And there's some parameters on the spacecraft, the few that we'll use here. It's about 300 kilograms, about 2 meters in diameter, 4 meters squared facing the sun. And of course, it's moving at about 30 kilometers per second, 1 AU, 2 pi over a year. That means the relative, you can't actually get that from here, but this will apply to a Lorentz force later, a disturbance with the magnetic fields. The relative velocity of the spacecrafts, because they're not at the Lagrange point, about 15 meters per second. You've heard all about the Doppler shifts and the trouble it makes for the laser heterodyne measurements. Here's a prettier picture of the Y tubes, and you saw this on Bill's slides last Monday.
I thought really velocities are more like 3 or 4 kilometers per second. It's really 15.
15 meters per second, the relative speed.
Meters per second.
Right.
It's really 15.
It can be, up to.
Up to 15.
Yep. Right, and that would produce the 15 megahertz Doppler shift on a 300 terahertz laser beam. And I know you've heard the 15 megahertz Doppler shift. So, here, now we get deeper into the spacecraft. Those are the Y tubes, and here's the optical assembly. Optical assemblies basically consist of the telescope, the optical bench, and a limited amount of electronics. You can tell this diagram came from the Europeans because they call it accelerometer electronics. Anyway, so now we get to the third stage of passive thermal isolation.
Understand this reference to accelerometer electronics?
Well, that's what I mean. I will go to great pains to explain that she's not an accelerometer and that eases our things. But all of the sensing and actuation heritage comes from accelerometers. So some of the diagrams still refer to it as an accelerometer.
But there also is a political issue.
Oh, I was keeping that quiet. You're welcome to bring that up. I did mention the Europeans made this picture.
Okay, go ahead.
And call it accelerometer electronics. But it would definitely make it much harder if we tried to function as an accelerometer. So there's a support cylinder that goes all the way around this. Again, it's a graphite epoxy, another item of low thermal conductivity, and that's our third stage. The fourth stage of passive thermal isolation, you'll see why I'm harping on this, because it happens to be that thermal problems are one of our biggest, is the ULE bench. Oh, that's this whole light blue thing. Here's the housing around the proof mass, and it's made of titanium. Vacuum enclosure there, and there's our proof mass. So I'm hoping somebody's going to ask, why titanium? All this emphasis on low thermal conductivity. Titanium is not particularly low thermal conductivity.
Why titanium?
Glad you asked that question. No, actually, you'll understand later. Once you get down to the proof mass and you've tried to make it as stable as you can, now the important thing is that any fluctuations that get into the proof mass distribute themselves rapidly and equally. So, in fact, there is some talk, especially if you want to go to very low frequencies, say a 10th or 100th of a millihertz, of not using titanium, but of using something for this area that's higher thermal conductivity. Not sure what that would be, but that's exercise for the student. Then we get to the proof mass, and right now the baseline idea is that it would be an alloy of platinum and gold, about 10% platinum and 90% gold. The reason for that is, firstly, but not most importantly, is that it gives a high density. But definitely most importantly, and you'll see why, is that it gives an almost zero magnetic susceptibility. It comes from the fact that gold, if you look this up in your table of atomic susceptibilities, which I hope somebody has a handbook of chemistry and physics, because I want to look up sapphire. I can't get that in my little table of atomic susceptibilities. Gold has a negative, it's diamagnetic. It has a small and negative magnetic susceptibility, but platinum has about 10 times larger and positive. You add them together and you get almost zero, not quite. And the reason I bring that up is there was a question last week when we talked about wanting to make the proof mass very smooth for a reflective side, various other properties. Why did we make it out of quartz, ULE, or sapphire? I don't know about sapphire, but I know quartz. If you look up those, silicon is slightly diamagnetic, slightly negative, but oxygen is very, very positive magnetic susceptibility, and it would blow this, it would just ruin this part of it. So if somebody wants to look up sapphire and tell me, that would be good. And in the meantime, the reason we use platinum and gold is primarily for the very low magnetic properties. The mass is about 1 kilogram, area 16 centimeters squared. And the whole thing, there's been various names for it: inertial sensor, gravitational sensor. I think the best liked one now is a free mass sensor for the proof mass and the housing electronics. We're not going to go through this, but when you do homework problems, you might need all these details. All the details about the spacecraft and the proof mass some constants you might have forgotten. I doubt it, but maybe, in the laser. Okay. So here are the very basic requirements. Number one, each proof mass, and I'll tell you where these come from. Each proof mass must remain free of acceleration disturbances other than gravitational waves, down to about 1/3 of a femto-g per root hertz. And of course, this is only true in the lower end of the bandwidth measurement, maybe 10 to the minus 5 hertz, but certainly 10 to the minus 4 hertz, up to about 10 millihertz. Secondly, each proof mass has to remain centered within its housing to about 300 picometers and millihertz, and aligned with the measurement optics to roughly 30 milliarc seconds. So what's the general approach to these general requirements? Well, first of all, find out what all the disturbances are, both from the spacecraft and the space environment. That means the sun and the interplanetary magnetic field and cosmic rays. Minimize them in whatever way you can think of, other than talking to God and changing the cosmic ray flux or something. And then isolate the proof masses if you can. Secondly, since we know there's this DC force from the solar flux on the spacecraft, you know that if you don't do something, they're going to jam right into the proof masses. So some sense you're going to have to move the spacecraft, and we're not going to move the proof masses, at least along the plane of the measurement. And secondly, out of measurement plane, as necessary, in a limited way, we'll actuate the proof masses to keep them centered in the housing. So the general challenges to this general approach to the general requirements are, one, somehow you have to monitor the proof mass spacecraft relative position and attitude. That's 6 degrees of freedom per proof mass, 2 proof masses per spacecraft, 3 spacecraft, mounts up quickly. Secondly, you have to control the spacecraft position, and you've already heard about the micronewton thrusters that we'll plan to use that get their information from the position sensors, which we have yet to decide what these are. Thirdly, somehow you're going to control the out-of-plane proof mass motion without coupling into the crucial measurement plane. And fourthly, I already alluded to the fact that temperature fluctuations are a big problem. That's a big general challenge. So the obvious questions to be answered after we've handed this challenge to the grad student is, first, what are the sources of disturbance and how can you minimize them? There are several ways for each. What are the resulting requirements on, and this is what the engineer gets asked. First of all, are proof mass sensors and actuators. How sensitive do they have to be? How accurate do they have to be, both in terms of knowledge and control? And secondly, when it comes to the spacecraft control loop, how good does that have to be? Meaning, how high does your gain have to be? How quiet do your thrusters have to be? And we have to get enough handle on the whole problem that we can answer these questions. So it isn't just an exercise in laying out the general equations. The specific technical challenges you'll see very quickly here as we get into the disturbances. Number one is a very high thermal stability. Across the spacecraft, the solar fluctuations themselves will cause about 1/10 of a Kelvin per root hertz. We need passive isolation and thermal shields just on the spacecraft itself to bring that down by a factor of 100. That needs to be brought down by a factor of almost 1,000 more across the proof mass before you get to this titanium housing. The reason for that is twofold. Across the spacecraft, if you have, it's mostly aluminum, which doesn't have a very low CTE, coefficient of thermal expansion. So if things distort thermally, you change the effective gravitational force on the proof mass and it looks like a gravitational wave. And secondly, if it isn't stable across the proof mass housing, then you have differential fluctuations from radiation pressure, thermal radiation pressure, not to mention the laser radiation pressure on the proof mass. Another challenge, which has to do with the proof mass and its low magnetic susceptibility, we also have to keep any gradients of the local magnetic field in the spacecraft down. That's not so easy, considering you have magnets on the laser that work as Faraday oscillators to keep the frequency stable. You also have currents in different directions, right? So Ampere's law and Biot-Savart law, that gives you a fairly high magnetic field in the spacecraft, and the gradients are high because it's only 1 meter across.
How high?
How high
are the local fields?
Oh, they're going to be about a microtesla or larger. You see, we'll drive it in just a moment. You'll drive it. We need an excellent vacuum. That sounds easy. You just vent it to space. But they're kind of worried about using explosive volts to vent this to space, because pyrotechnic devices tend to leave shrapnel, or whatever you call it. So what's that thing goes in your leg when you get, anyway, so that's not so good. So there are various other schemes, but if they can't do that, then they have to rely on getters. Is that what they're called? Things that suck up all this stuff. Anyway, we need to keep it down to about a pico atmosphere, from collisions with residual gas.
But isn't the residual gas going to go away?
Oh no, the material's outgas. It gets worse and worse. Worse and worse as time goes. The material's outgassing. So you either vent that to space or you use getters to suck it up. About a micropascal, it doesn't seem so hard. But getting down another factor of 3, they start to think that the getters can't do it. I know, you wouldn't have thought that would be a problem, but we require such an excellent vacuum that it is a problem. A fourth challenge is that the proof mass will acquire charge just from cosmic ray impacts. And eventually, if that gets too high, because the proof mass is moving through space, it couples to fluctuations in the interplanetary magnetic field. And unfortunately, these fluctuations have a frequency dependence. They go up like 1 over frequency. So although this isn't a problem in a millihertz, it's a huge problem, or a significant problem, maybe the second or third largest problem down at 100th of a millihertz. It also couples to voltage fluctuations in a capacitive sensor. In fact, just about everything that fluctuates in a capacitive sensor causes us trouble, which is why the motivation to look at some other possibilities for sensors. The final specific technical challenge I want to preface here is patch field potentials on electrodes. Anytime you have a metal electrode, just because they can't lay out perfect crystals on gold, for example, there are variations in the work potential of the material itself. So you have effective DC potentials, but they're maybe on millimeter scales on the material itself, sometimes smaller. These couple to fluctuations of the charge on the proof mass, because there's fluctuating Poisson, if you will, impact rates of the cosmic rays. It also couples to proof mass spacecraft motion, so it contributes to a coupling constant. We'll see that in a minute. Generally, you remember this. If you just take away this sensitivity curve for a minute, and suppose that the scientists presented you the gravitational wave physics, Kip said, hey, look at all this. You guys figure out a way to see as much of this stuff as you can, and particularly we want to see stuff down here because LIGO's up here. So, and if somebody told you, consider a Delta II launch vehicle so you can't have telescopes more than 30 centimeters, you come here, you do your quick little quantum shot noise calculation on various arm lengths, and you'd say, well, if I could get it right about here for shot noise on a measurement, that would be good. I'd get everything above that. And then Kip would remind you that you get out here, if you're going to use 5 million kilometer arm lengths, you get out here and suddenly your gravitational waves are shorter than your arm length, so you're going to lose it here. And then somebody else like Pete Bender would come along and say, well, wait a minute, you've got all this physics bothering you, all these disturbances, and even if you're going to call it white noise, at some point a white noise acceleration leads to a 1 over f squared displacement noise. So at some point that goes up. So we'll see where this comes. I won't go through this in detail, but you can, or at least you have a reference to prove it to yourself. If gravitational wave physics says we'd like to be sensitive for frequencies under 30 millihertz, that tells us that we need arm lengths in an interferometer that are at least 5 million kilometers apart. If we tell you you can't afford more than the Delta II launch vehicle, that's going to limit your telescope sizes. Technology says, well, let's see, the optics efficiencies are really best at about 0.5 to 1 micron. Laser power with pump diodes is probably best at about 1 micron, because if you double it, you lose power. So that gives you your telescope size and your laser frequency and your laser power. And given that, then quantum mechanics limits your optical interferometric measurement to about 10 picometers per root hertz. Your Fresnel factor, because we're in the far zone, is about 2 times 10 to the minus 10th. You've seen that and seen how it scales. And your received power is about 60 picowatts. And that's one way, actually. No, yeah, that's one way. So here's your expression from there for your measurement accuracy or precision, to be more correct. It's about 10 picometer per root hertz. And again, you've heard this twice. If you didn't have a transponder and you had to deal with 1 over R4, you'd get about 200 photons an hour. You'd never measure better than a micron per root hertz. So this is consistent. Take it right from here with a strain of about 8 times 10 to the minus 21, the factor of 4 from a round trip measurement in 2 arms. Because you subtract the 2 arms because the gravitational wave signal should be more or less opposite in sign. And that gives you this h times 10 to the minus 23rd, which is here. So there's your quantum noise limit. Exactly what we said when we integrate for a year. But now we talk about Pete Bender's white forces. If you don't know Pete Bender, he's a wonderful guy from Colorado who always has some piece of physics to remind you of when you think you're going to get a free lunch. And because somebody did enough physics to realize that you were dreaming if you thought you could get them smaller than 1/3 of a femto G per root hertz. That left that other line. That left this line. And the quantum mechanics left this line. And the gravitational wavelength left this problem, and so there you're left with your Lisa sensitivity curve, which Shane has on the web in a much more beautiful way, and you can tweak it all you want and play with it. But the point is that this goal of 3 times 10 to the minus 15 meters per second per root hertz is at least 6 orders of magnitude more difficult than anything ever demonstrated or even planned. And this is the heritage I'll go through later if we have time, because it's fun history and it has really pretty pictures instead of equations. But this was something done by Stanford and Johns Hopkins for the Navy in '72. Grace just launched, up here around 10 to the minus 9 per root hertz. The GPB, we shall see. Ujvash is a ground demonstration experiment with a torsion pendulum, down here around 5 times 10 to the minus 13. DRS is ST7. It's a new millennium project to be launched in about 4 years.
So this is the Lisa test.
The Lisa test package, all the different names for it, ST7. It's kind of confusing, but they decided to name it DRS, which is problematic for me, but anyway. And then here's Lisa. Okay, just a little reality check here on what this means. When we talk about 10 picometers per root hertz and 3 times 10 to the minus 15 meters per second squared, let's take a 10 millihertz bandwidth in Lisa. So that means that we don't want, in that bandwidth, she's not to move more than 1 picometer. She's not to have pressure fluctuations more than 1/4 of a piconewton per meter squared. She's not to have force fluctuations more than 40% of a femtonewton. What is this? All right, so here's just a few facts to remind you for fun. That 100 micronewtons per meter squared, when we talk about pressure, is like a barely audible whisper at 2 meters. If we look at the DC solar pressure, it's about 10 micronewtons. And all I've done here is taken the solar constant, taken the worst case of 2, which is a perfectly reflecting spacecraft. The best case would be a factor of 1 if it were perfectly absorbing. And I come out with that DC solar pressure. That's about a barely audible whisper at 6 meters. So the DC force on the spacecraft with a 4 meter squared area is about 4 milligrams. Which is about 8.8 micropounds, which is like 1 micro cat, my big cat, which is about the weight of 2 3-punch paper holes. Now we go to the fluctuations in the solar flux, which are about 0.1% at a millihertz, and they scale as 1 over frequency to the 1/3 power. There's about 1.3 nanonewtons. That's like a whisper at 1/2 kilometer. And the fluctuating force on the spacecraft is about 1/2 micro G, or about 500,000 bacteria. But that's the spacecraft. What are we demanding for the proof mass on Lisa? We're demanding a pressure fluctuation no greater than a whisper at about 25 miles. That's like somebody at the top of Catalina runway.
1 over 500,000 of the bacteria.
What?
1 over 500,000 of the bacteria, right?
Yes, 1/2 of a microgram. Yeah, 500 nanograms. I think this is roughly, I suppose it depends which bacteria we're talking about. Giardia or something, I think it's what it
But it should be 1 over 500,000, not like,
No,
no? Oh.
no, it's 500,000 bacteria. The bacteria are lighter. Bacteria are about a picogram. Giardia, what I looked up. You may have larger bacteria than I do. And anyway, and the maximum force fluctuation on the proof mass is about the weight of 1/25th of a bacteria. So this is very sensitive growth. All right, so we talked about accelerometers. Forgetting the political problem, let's see the advantages of why she isn't. What does an accelerometer do? It tries to measure the non-gravitational forces on the spacecraft, or whatever is your final object of interest, via servo-controlled test mass, or proof mass. The Triad did it on a spacecraft with a spherical proof mass. They isolated and monitored the proof mass very carefully, forced the spacecraft to follow it, and from that they inferred all the non-gravitational forces that were acting on the spacecraft. All the gravity gradiometers on Aristoteles, for example, they're all doing that. And once you try to do that, when your basic data is your acceleration, it's not that you're trying to do something and just minimize the acceleration, but you're actually trying to measure what the acceleration is. Then you have to minimize the disturbances to both the spacecraft and the proof mass. Because the acceleration is your data, your final data, there are very stringent requirements on the linearity, the stability, and the scale factor accuracy of your sensors. Your readout sensitivity has to be very high. For gradio, which is the gravity gradiometers, the capacitive accelerometers used on Aristoteles, they needed 6 picometers per root hertz. It's about 3 orders of magnitude more than LISA needs. See, LISA's easy. You need a very strong coupling between the proof mass and spacecraft because they have to respond to each other quickly and tightly, and yet you want no back action. That means that if you're using capacitive sensing, the gaps between the proof mass and the electrode are very small. On gradio, again, they were 30 microns on 2 sides and 300 microns on the bigger side, the sensitive side. Small gaps means very large disturbance from any fluctuations in the voltages on the electrodes or the charge. It's just hard, really hard. So here, for the first time, maybe the only place this entire lecture, something is going to look easy for LISA. All we care about is minimizing the disturbances to the proof masses. And we just say, okay, keep the spacecraft reasonably centered around the proof mass. That's all. A readout sensitivity of about 1 nanometer per root hertz is quite sufficient in our bandwidth. We want a very weak coupling. We really would just assume the proof mass didn't know the spacecraft was there. We need proof mass sensing for 6 degrees of freedom, but really we're only going to actuate in 5, and that very limited. So large gaps are fine. Large gaps are good. The baseline design right now is capacitive sensors and actuators, only because that's the only heritage, essentially, that we have. So they're the type that were used on Aristoteles, gradiometers. Again, they're a gold and platinum alloy, about the same size as for LISA, but we can use 2 millimeter gaps. We still have serious noise from the fluctuating charge, patch field potentials, especially at low frequency, because some of those effects go as 1 over frequency. So we need to explore some other options.
So you increase the gaps to 2 millimeters from 300 microns in order to get these fluctuating forces from charge fluctuations and so forth down.
We would like to increase them still further, but the question is whether they can then get the readout sensitivity that's needed, and they can't. It looks problematic. If you move them away to get rid of the disturbance, now suddenly you don't have sensitivity. So there's strong motivation for that reason to go to perhaps some other sensors, and maybe even some other less invasive actuation. Now, it's a great way to cage it and suspend it, and maybe even control it forcefully to initialize it. But after that, you'd like to move them away and find some other less invasive way to sense it. And there's also an option of using a sphere instead of a cube. I'll go into that briefly later because I'd like to spend some time on the physics. So I'm going to go into the control model. Even though this is boring equations, it gets to some really fun physics, I think, anyway. It'll make you remember everything you tried to forget from Physics 106. If you took it here at Caltech, I think, is it still 106? It's still 106, yeah. 106 and 209, all right. So first of all, we're going to make some simplifications. We're going to consider one control system at a time, meaning I'm just going to control the spacecraft. Let's forget about controlling the proof mass for now. One direction at a time, okay, along a measurement axis. Let's just say one proof mass. I'm going to look at the picture. Here's a little picture of it. Here's the proof mass. Here's the spacecraft. I have external disturbances to the spacecraft that come from space and also from my own thrusters. and maybe a little bit from the proof mass. Very little recoil to the spacecraft from the proof mass, but not so as the opposite. The proof mass also gets direct disturbances. I call them ANP as opposed to ANS, and thruster noise NT. It also is coupled to the spacecraft. And here I've got proof mass leading to a displacement XP of the proof mass. Displacements, these are just fluctuations of the spacecraft. They get added, differenced, if you will, in our displacement sensor. And then, of course, there's readout noise in our sensor. That readout noise transfers into the thrusters because it's an error you put in your drag-free control loop. Goes back to the spacecraft and maybe adjusts the spacecraft slightly wrongly. And it feeds back in that loop. But let's forget about this loop for now because I'm not going to actuate the proof masses. So nothing is coming back in the next few graphs and the rest of this lecture. Nothing is coming back from our sensors to our proof mass for now.
Yeah? It's not going to come back through the whole lecture?
Well, not in the equations. We can stay after if you like and discuss that. Okay, so you've got the spacecraft external disturbances and recoil from the proof mass plus its thruster noise. In the plane of the interferometer, I said the proof mass has two types of disturbances. There are the ANP, the direct ones from space. I've already talked about some of them, the thermal radiation pressure, cosmic ray impacts, residual gas pressure, laser radiation pressure, magnetic forces, because it's not completely diamagnetic, and it is a moving charge in a magnetic field of the interplanetary field, the gravitational thermal distortion and electrostatic forces from the sensor. It also suffers from recoil, both from our sensor and from the spacecraft itself. And those motions tend to be linearly dependent on whatever that separation is, or fluctuations in that separation. So it's like a spring-like stiffness. That comes from gravitational gradients. Let's say you have a disturbing mass outside the proof mass and it moves. All right, so that's a force that actually depends on that displacement. So that's like a spring. And a potentially larger one comes from gradients in the capacitance of the sensor. So that's the picture. And now all that remains really is to do a bunch of physics and calculate all the things that could be there and what does the number add up to. All the things that could be for the spacecraft, what does that add up to? An estimate of thruster noise from the laboratory, an estimate of readout noise from whatever sensor you use in the laboratory, and then it just remains to calculate AP. And maybe we'd like to know what the final acceleration noise to the spacecraft, AS, is as well. Of course, we'd like to know what this effective coupling constant is. We'll get that from physics. So when we do all that, and and by the way, these little boxes, these little transfer functions, you can just tell what their units are. Some of them are dimensionless. For example, you take the relative displacement of the proof mass in the spacecraft, XPS, it comes out with readout noise and it goes into a displacement sensor R. It comes out as a force. So R as a transfer function is going to take displacement meters into force. So you know that, for example, R and K for that matter too are going to have dimensions of 1 over second squared because they take position and put an acceleration out. The thruster noise takes an acceleration in and puts out an acceleration, so it's dimensionless. And the proof mass and spacecraft dynamics, these little boxes, they take acceleration in and put a displacement out. So nominally I'll say that they're 1 over omega squared. That's a rather simplistic assumption because they may have some complicated frequency dependence, but at the bare minimum you know that they have that frequency dependence. So then just solve the equations and assume that they're linear, and that's your first homework problem, or you can check that paper, and you get solutions for the final acceleration noise on the proof mass, the spacecraft, and the effective acceleration of the proof mass spacecraft gap, XPS. And all that's really important from these equations right now is that you see that first there's a dependence on the external noise to the proof mass, which is all the physics we calculate. Secondly, there's a dependence on the readout back action. We take that from whatever the sensor can do and note that they're multiplied by different factors. And then there's a contribution from the spacecraft noise and the thrusters. So all that remains is to calculate from physics what these are, take what your sensor can do, calculate what your spring-like coupling is, get the spacecraft acceleration noise from physics, and get the thruster noise from whatever they tell you at STEC or whichever thruster you're using, and you're done. Then, what does done mean? It means you're going to set a limit on the spacecraft control loop gain, which is going to be equal to the product of your transfer functions, U, and it comes in here, there. And you're also going to put a limit on your sensitivity. And notice that if you find a limit, just by saying that each of these terms has to be smaller than, say, 1 times 10 to the minus 15 meters per second squared per root hertz. And notice here that if you find a limit for your readout sensitivity, you've also found a limit for the relative motion of the proof mass in spacecraft. There's just those equations again, and these are the 5 things we want to calculate or pull from somebody's laboratory demonstration. 3 things I want to note here, and we'll come back to the accelerometer issue. You'll see it in a moment. First of all, when you look at the acceleration, the final acceleration to the proof mass, here are the direct disturbances from space, I said. And these are the so-called indirect ones from the spacecraft and from the back action from the readout sensor. Notice that the indirect disturbances are all suppressed relative to the direct disturbances by these small factors. The coupling to the spacecraft, or the coupling to the spacecraft divided by the spacecraft control loop gain. So of course we want this dimensionless coupling, k over omega squared, to be smaller than 1. That means, say, at 1/10 of a millihertz, that k has to be, the spring constant, less than 10 to the minus 7 per second squared. That's about what they say they can give for capacitive sensors. Not less than that, but that. I give an argument that says maybe, theoretically, it could be 50 times smaller than that. But that's purely theoretical, and nobody's shown that in the lab yet. Secondly, and here's the accelerometer thing, look at the net acceleration to the spacecraft and see how it depends on sensor noise differently than the proof mass did. If we make this dimensionless coupling, k over omega squared, which is too high for me, if we make that very small, that's what multiplies your readout sensitivity for the proof mass. That means that what multiplies your readout sensitivity for the spacecraft is not so small. If this were an accelerometer, you'd want to operate at k over omega squared equal to 1, so that these terms would go away, and your net acceleration on the spacecraft would be exactly what your proof mass feels, because that's what you wanted to find out. So you really, optimally, as an accelerometer, you would only operate at 1 frequency, and you'd have to design your spring constant to be equal to it. Not so with LISA. A spacecraft is going to see a lot more back action from the readout sensor. The point is we don't want the proof mass to see it. That's why we want a very weak coupling, but in the case of an accelerometer, this would not be weak. I've probably drilled that one to death. And then finally, the third point was that whatever your required readout sensitivity, it's roughly the same as your allowable motion between the proof mass and the spacecraft. So that's another way to go back, because what people want to know is, some people want to know how good my readout sensor has to be, but what people who are building the thing want to know is, how much can this wiggle? And if they're the same, that's just an easy answer. Yeah.